If you're an anesthesiologist or a surgeon, particularly a plastic surgeon or a dentist or an ED physician, and you inject local anesthetic into your patient, you need to understand the pharmacology of these particular agents. In this tutorial, the first of three, we're going to look at the basic physical properties of local anesthetics and how the environment in which you inject a local anesthetic may change the effectiveness of those particular drugs. Now, this gets a bit sciencey and you might find it a little bit difficult and confusing, but don't worry, everybody else does as well. That doesn't mean you don't need to know this stuff. If you're a trainee in anesthesiology, this is core curriculum material. Anesthesiology Tutorials with me, your host, Pat Nelligan. This is the first tutorial of three on local anesthetics. Local anesthetics are drugs that produce reversible depression of nerve conduction when applied to the nerve fiber. They are sodium channel blockers and they work from inside the neuron. They block motor, sensory, and autonomic nerves and work in the central, peripheral, and autonomic nervous systems. Local anesthetics have been around for a long time. Originally, they derived from coca leaves. The Incas in Peru chewed coca leaves, causing numbness and a stimulant effect, and they were brought to Europe in about the 1850s. In 1860, Albert Niemann isolated cocaine from coca leaves. So cocaine became the first local anesthetic as we know it, and it was first used in 1884 by Karl Koller, who was an Austrian ophthalmologist who used it for topical local anesthesia for glaucoma surgery. That led to a landslide in the use of this particular drug. It was rapidly adopted in eye and dental surgery, but there were two major drawbacks. The first was that it was highly addictive, and secondly, it was highly toxic. Many deaths were associated with its use. And as a consequence, a whole series of other drugs based on cocaine were developed, and these were known as the amino esters: benzocaine, amylocaine, procaine, known conventionally in the popular literature as novocaine, chloroprocaine, and tetracaine or amethacane, a drug that's still used today. The problem with these drugs was twofold: allergies, because they were esters, and short duration of action, meaning that they weren't great for doing regional anesthesia and prolonged nerve blocks. From the 1940s onwards, drugs that you will be very familiar with became the de facto local anesthetics of choice. And the first and most important of all of these was lidocaine. It's also sometimes known as lignocaine, but it should be called lidocaine these days, or xylocaine, the trade name. That was followed by mepivacaine, prilocaine, and then the big one, bupivacaine in 1957. Later, because of problems with bupivacaine and toxicity, ropivacaine and L-bupivacaine were developed. Today, the drugs you're likely to use are lidocaine, bupivacaine, ropivacaine, L-bupivacaine, otherwise known as thyrocaine, and occasionally prilocaine. Just one thing that you should know when you administer a local anesthetic: when the dose increases progressively, nerve fibers are blocked in a sequence. The first fibers to be blocked are the autonomic B fibers, then the sensory fibers, the A delta fibers and the C fibers, followed by proprioception and then alpha motor neurons. So that with careful titration of the dose, sensory neurons can be selectively blocked due to their narrower diameter, thin myelin sheets, and more frequent nodes of Ranvier. So the strategy with using local anesthetics is about getting the right dose to the right place and the right concentration at the right time. To understand how this works, you need to understand the pharmacology of local anesthetics, and there is no way around this. If you work in anesthesia or surgery or dentistry, you need to understand local anesthetics. I'm going to show you a case now that's a little bit difficult, but if you understand how this case went, you understand so much about local anesthetics. You're in the operating room, and Callum is a 59-year-old type 1 diabetic with a gangrenous foot. He's scheduled to undergo forefoot surgery because that's gangrenous, but he still has sensation, so you decide to do an ankle block, and you administer a generous quantity of local anesthetic under ultrasound guidance. 30 minutes later, despite you seeing a donut of local anesthetic around the nerves, he's still able to move his toes. Why did the block appear to fail? To understand how local anesthetics work, you need to be familiar with the behavior of charged compounds that are diluted in liquids. Acids are compounds that, when inserted into water, dissociate to release a hydrogen ion. Not every molecule of these compounds dissociates, and the strength of the acid is determined by the degree of dissociation. The more dissociated, the stronger the acid. Following dissociation, the ionic particle carries a negative charge. Hydrochloric acid, which is a hydrogen ion, and chloride fully dissociates in water, so it's a strong acid, and the amount of acid present can be measured by the quantity of chloride. A base is a compound that, when inserted into water, releases a hydroxyl. Not every molecule of this compound dissociates. The degree of dissociation determines the strength of the base. A partially dissociated base is a weak base. A fully dissociated base is a strong base. Following dissociation, the ionic particle carries a positive charge. Sodium hydroxide is a strong base. It entirely dissociates in water. You can measure the quantity of the base by measuring the quantity of sodium ions. The pKa is the pH at which the compound is 50% dissociated or 50% ionized. As a consequence, the pKa versus the local pH, and that can vary, determines the degree of dissociation or ionization. In this situation, we have a sample of arterial blood, and into that we are going to insert a compound that has a pKa of 6.1. Is this an acid or a base? If the pKa of a compound is below the prevailing pH, that's usually based on water, which is a pH of 7, but blood has a pH of 7.4, then it must be an acid. With a pKa of 6.1, that seems to be very close to 7.4. Is this a strong or a weak acid? This is a weak acid, and I'll explain why. Let's draw a cartoon. This line represents the percentage association, 10%, 50%, and 100%. As one moves upwards, the compound is less ionized and more associated, and as one moves downwards, the compound is more ionized and less associated. On the x-axis, we're going to draw pH. In this direction, the pH is lower, and in this direction, to the right, the pH is higher. We draw a line right in the middle there. This line represents the pKa, where the compound is 50% associated and 50% dissociated. So that pKa is the pH of 50% association. Consequently, the lower the pH, the more associated the compound, and the higher the pH, the more dissociated the compound. A strong acid, for example, may have a pH of 2 or 3. A weak acid would have a pH of 6. So this is a weak acid. If the pKa was 3, it would be a strong biological acid. Now let's look at a different compound. This compound is a pKa of 8.1, and we're going to dissolve it into blood with a pH of 7.4. Is this an acid or a base? Because the pKa is above the pH, it must be a base. Is this a weak or a strong base? Well, we need to look at that. Alkali are the opposite of acids. Again, the pKa is the pH at which the particle is 50% associated and 50% dissociated or ionized. As the pH falls, the compound becomes more ionized. This particle, a local anesthetic with a pKa of 8.1, remember, pKa 50% associated and 50% ionized. And when it's inserted into blood with a pH of 7.4, it becomes more ionized, going from 50% ionization at pKa to 83% ionization at 7.4. In this situation, we're going to insert our local anesthetic into intracellular fluid where the pH is 6.8. This is the same base with a pKa of 8.1. Is this base more or less ionized at this pH? Let's look at what we've learned so far. The pKa starts at 8.1 with 50% dissociation. As the pH is lowered, the compound becomes more ionized, so that at 7.4 it is 83% ionized. Now we are going to reduce the pH to 6.8. As you would now expect, the compound becomes even more ionized. At this pH, it is 95% ionized and 5% unionized. So in summary, as the pH falls, acids become less ionized and bases become more ionized. Local anesthetics have pKa's between 7.7 and 8.3, so all local anesthetics are weak bases. If you look at the chemical structure of a local anesthetic, there are three parts. An aromatic part that's typically fat soluble, a middle part that is either an ester or more typically these days an amide, and an ionizable part that is a tertiary amine. Simply, there is a fat-soluble bit, an intermediate bit, and a base bit. And the degree of dissociation of that base bit is determined by the pKa. This combination is critical to the functioning of local anesthetics because they are amphiphilic. Fat solubility allows the local anesthetic to enter nerves. Ionization allows the local anesthetic to dissolve in water or blood. Key to understanding local anesthetics, and indeed any drug that works on nerve tissue, is to keep in mind what the nerve cells look like. The outside of the cell is lined with the lipid bilayer. Ionized compounds cannot enter the cell unless they are carried by specific transport proteins. Conversely, fat-soluble, uncharged compounds can pass relatively easily into the cell interior. One of the major problems with fat-soluble drugs is that they are very hard to prepare in a safe and injectable product. For example, propofol requires a lipid emulsion. Hence, it is customary to manufacture local anesthetics which are weak bases as hydrochloric acid salts. In the salt, negatively charged chloride binds with a positively charged local anesthetic. Local anesthetics are products with shelf lives, so they have to sit on a shelf for a long time before you pick them up, and the best way to do that is to dissolve the local anesthetic in water. But because they're weak bases and water is a pH of 7, there will be only partial ionization and poor solubility. To ensure good solubility and stability in the solution, they're prepared as hydrochloric acid salts. The hydrochloric acid reduces the pH of the solution and results in full ionization. These are the widely used local anesthetic agents, and you can see that they are prepared in hydrochloric acid solutions. Now, the next part is a bit sciencey, but I believe that you need to recognize the preparation to understand how these drugs work. This is water, and water is slightly ionized to release hydrogen and hydroxyl ions. They're really globs of water with a bit of hydrogen or a bit of hydroxyl attached to it. The pH is 7.0, which means at that level, the hydrogen ion activity and the hydroxyl ion activity are equal, with a charge of approximately 100 nanoequivalents per litre. What we're going to do is we're going to insert local anesthetic and chloride salts. So the chloride is bound to the positive part of the local anesthetic, the weak base. When that is inserted into water, the salt immediately ionizes, releasing chloride and free base. Chloride is a strong anion, and hydrochloric acid has a very, very low pKa, resulting in chloride being fully ionized. The local anesthetic is a weak base, so it will bind up with a significant amount of hydroxyl present in water. Because the ionization of chloride is 100% and the ionization of the local anesthetic is low, the pH falls. As the pH falls, the degree of ionization of the local anesthetic increases, eventually equalizing the pH of the liquid to 6. Returning to the graph that I showed you previously with reference to bupivacaine. Bupivacaine has a pKa of 8.1 and the pH of water is 7. At this pH, bupivacaine is about 95% ionized. That is not enough for stability. By combining bupivacaine with chloride, the pH of the liquid falls to 6. As a consequence, the bupivacaine will be fully dissociated at that pH level. These are the referenced pKa's of commonly used local anesthetics, and they're easy to remember. You can see that lidocaine and prilocaine, both rapid onset local anesthetics, and this is important, have pKa's of 7.9. For the longer acting agents, the pKa's are 8.1. Those agents are bupivacaine, L-bupivacaine, and ropivacaine. There is a good reason why these pKa's are different with reference to the onset of action. Now we're going to look at what happens when you inject local anesthetic and why the pKa matters so much. It is elegant pharmacology. First, you need to recognize that the pH of well-perfused, well-oxygenated tissue into which you're injecting the local is the pH of extracellular fluid, and that is 7.4. The contents of the syringe are at a pH of 6.0. At that pH, nearly all of the local anesthetic is ionized. Now, we're injecting the local anesthetic, and immediately there will be a chemical change in the liquid that is injected. At a pH of 6, bupivacaine is nearly 100% ionized. Once the local anesthetic has been injected into the tissues, then the chloride diffuses away and the pH in which the anesthetic is injected rises. The result is that the drug becomes more associated, in this case to about 17%. In this state, the drug is significantly more lipophilic. And that matters because a lipophilic drug can pass through the myelin sheath, the cell membrane of the neuron. How does this affect nerves? Nerve action potential occurs when sodium enters the cell, facilitating electrical activity, and an action potential ensues. The ionized local anesthetic cannot easily enter the neuron. However, that 17% of unionized local easily enters the neuron, and that is where things become even more interesting. Because inside the nerve cell, the pH is 6.8. Now that the drug is inside the cell with a lower pH, the local anesthetic rapidly dissociates into free base. And now it's approximately 95% ionized. So inside the neuron, the drug ionizes, the ionized moiety then blocks the sodium channel from the inside, and sodium is unable to pass through the channel. The nerve action potential is stopped. And that's how local anesthetics work. All local anesthetics block sodium channels from inside the neuron. For them to work, they have to cross the cell membrane and then ionize within the nerve cell. So while they all work the same way, some have a rapid onset and offset of action, some have a longer duration of action. So let's look at the pharmacological properties that influence local anesthetics. The first property relates to its pKa. The lower the pKa, the ion dissociation constant, the more rapid the speed of onset, because at a lower pKa, there is more unionized drug. Returning to this chart, I have now put a second column in that represents the percentage of drug that is unionized at 7.4. Remember, the closer the pKa is to the pH, the higher the percentage unionized. Lidocaine and prilocaine with pKa's of 7.9 are 25% unionized versus bupivacaine, which, as we have seen, is 17% unionized. Because there is more of the drug that is unionized, there is more of the drug that is fat soluble. So those two agents, lidocaine and prilocaine, enter the neurons faster than bupivacaine, L-bupivacaine, or ropivacaine. They have a more rapid onset of action. The duration of action of local anesthetics is determined by protein binding. The principal protein that binds local anesthetics is alpha-1 acid glycoprotein, but tissue proteins also bind local. The more protein bound, the longer the duration of action. This takes a bit of explaining. Only free drug is active. Local anesthetics must diffuse across membranes and bind to sodium channels inside the nerve cells to exert their effect. Protein-bound drug in the plasma and in the interstitial space is inactive until it dissociates from protein. Once bound to protein, that slows the clearance of the drug, so high protein binding reduces renal and hepatic clearance because protein-bound drugs are not filtered or metabolized as easily as free drugs. That results in a longer half-life and sustained plasma levels. In addition to plasma protein binding, principally with alpha-1 acid glycoprotein, bupivacaine, for example, binds extensively to tissue proteins, particularly in fat and myelin-rich nerve tissues. This allows slow, prolonged release at the site of action. This table shows you the percentage of the drug injected that binds to protein. The lowest protein binding is with prilocaine, 55%, and then lidocaine, 65%. So these are both short-acting drugs. For bupivacaine and its derivatives, L-bupivacaine and ropivacaine, that protein binding percent is in excess of 90%. For thyrocaine, L-bupivacaine, it's 97%. That's all at a pH of 7.4. When lidocaine is injected, a significant portion enters the nerve cell and affects the block. Some of the free lidocaine is absorbed by lymphatics or veins and transported to the liver and kidneys for disposal. A modest amount is bound to fat and protein. Conversely, as bupivacaine is slow to enter cells, it has a far higher affinity for both protein and fat. Less is carried away and more of the free drug is stuck to the tissues in and around the nerve cells. The major advantage of this is that the fat and protein acts as a reservoir for the drug, prolonging the duration of action. The potency of local anesthetics is determined by lipid solubility. What I mean by potency is how much or how little drug it takes to have the same effect. An example from perhaps your own life is looking at the potency of whiskey versus beer versus wine. Alcohol in whiskey is about 40% by volume. In light beers, it's about 4%. So whiskey is 10 times more potent than beer, and it's about 4 times more potent than wine. The higher the lipid solubility, the more potent the drug. Now, I've decided not to provide a table of lipid solubility of local anesthetics, as every textbook and journal that I've looked at provide me with different numbers, sometimes partition coefficients, and I find it extremely confusing and unhelpful. Take it from me that highly lipid soluble agents are more potent. Consequently, what you need to know is that lidocaine and prilocaine are relatively equipotent. Ropivacaine is approximately 2.5 times more potent than lidocaine, and bupivacaine and L-bupivacaine are 4 times more potent than lidocaine. Why does that matter? Because when you're doing a nerve block, you need to know how much volume to give. But what's quite helpful is the way that the drug companies have provided us with these agents in 10 ml ampules. And the equivalent dose of, for example, 2% lidocaine in 10 ml is 0.5% bupivacaine, 0.5% levobupivacaine, 0.75% ropivacaine, and 2% prilocaine, all in 10 ml. If you use the dilute versions of these drugs, the equipotent dose, for example, for 1% lidocaine is 20 ml, for 0.25% bupivacaine is 20 ml, and for ropivacaine 0.375 is 20 ml. Why did Callum's block fail? Remember Callum, the diabetic with the gangrenous foot? You performed an ankle block 30 minutes ago, and now everybody is standing around looking at you because he's still moving his toes. Are you incompetent, or is there something else going on? The key to understand this situation is that a necrotic foot is underperfused and there is persistently high levels of lactate present. The pH of the tissues, even up to the level of the malleoli, may be significantly lower than normal extracellular pH. In this example, the pH of the tissues is 7. As a consequence, the pKa of the local anesthetic is further away from the pH, and as a consequence, the agent is more ionized and less likely to penetrate nerve tissue. When bupivacaine is injected into the tissues at a pH of 7, only 5% or less remains unionized. That means there is very little lipid-soluble drug available to affect a nerve block. The block may eventually work, but perhaps a spinal or a combined popliteal and adductor canal block may have been a better choice. Is there anything else you could have done? One thing that many anesthesiologists think is effective is to add sodium bicarbonate into the syringe immediately before injecting. Don't leave this lying around on the table. That increases the pH of the liquid to perhaps 7.8. The sodium bicarbonate alkalinizes the local tissue. It also makes the injectate more alkaline. The consequence is that more of the drug is in the associated form. In addition, the carbon dioxide that is generated by administering bicarbonate and locally buffering acid freely enters the nerve cells, forming carbonic acid, reducing the pH within. To summarize that, in a situation where you have infected tissue and you suspect that there's going to be a problem with the block, the pH of the infected tissue is lower, so there's more ionized local anesthetic and a much slower onset of action. By adding sodium bicarbonate, that will increase the speed of onset by alkalizing the solution and increasing the unionized fraction of the local anesthetic. By either adding carbon dioxide, there is a product out there called carbonated lidocaine, or just carbon dioxide that's being generated by the bicarbonate. That CO2 will pass into the nerve cells and it will reduce the pH within the nerve cell and increase the speed and quantity of ionization within the nerve cell, and that makes more local anesthetic available to block the channels. So in this situation, the pH drops from 6.8 to 6.6, and there is more local available to block the channels. The other time that you sometimes see sodium bicarbonate being used is in patients where you're giving them a little bleb of local to stick in an IV. That can be very, very painful, and if you add a small amount of sodium bicarbonate, that gets rid of the acidity of the solution and makes it less stingy. It'll also, of course, speed up the onset of the local anesthetic block. Finally, I thought I just might mention cocaine as a recreational agent, and one of the things you hear in the media is this concept of freebasing cocaine, and there is good science behind that. As you will recall, cocaine is usually prepared as a hydrochloric acid salt in powder or liquid form. And as a powder, it's principally snorted. The thing is, though, that hydrochloric acid keeps the cocaine relatively well ionized, which means that the onset of action of the drug is relatively slow. To form the freebase form, various chemical agents are used to wash away the hydrochloric acid component of the salt, resulting in free alkaline crystals. These are smoked, and due to their alkalinity, these particular crystals are almost completely unionized, so they're rapidly absorbed into neural tissue with presumably desirable side effects. Crack cocaine, incidentally, is cocaine plus baking powder, and again the baking powder is there to alkalinize the solution to increase the proportion of cocaine that is unionized. Let's review this tutorial. In this tutorial I discussed local anesthetics and explained that they are weak bases, and acid base is a huge component of how we understand how these particular drugs work. The pKa, the ion dissociation constant, determines the degree of ionization. Unionized particles enter the neurons more rapidly. The lower the pKa, the faster the onset and offset of action. Protein binding acts as a reservoir for local anesthetic. The higher the protein binding, the longer the duration of the block. Lipid solubility determines the potency of the drug. The higher the lipid solubility, the greater the potency. In the next tutorial, I will discuss the concentrations of local anesthetics versus activity, different local anesthetics that are available and when to use them, additives to local anesthetics, and the maximum safe dose of local anesthetics. I'll see you then, and I guarantee you'll learn something. So that's the end of the first tutorial on local anesthetics. I hope you found it useful. Next time we're going to look at drug doses, concentrations, and all the stuff that people put into their local anesthetics to make them apparently work better. If you're enjoying the tutorials, please subscribe to this channel and have a look at the treasure trove of videos that I have at CCM Tutorials. I'll see you soon.